Time. It governs every atom, every heartbeat, every star that burns across the void.
For centuries, we believed time was absolute, a river flowing in one direction, at one speed, for everyone.
But in 1895, H.G. Wells dared to imagine something extraordinary, a machine that could navigate time itself.
It was fiction then, but science was about to catch up. In 1905, a patent clerk in Bern asked a deceptively simple question. What would happen if you rode alongside a beam of light? That question shattered everything we thought we knew. It gave birth to the special theory of relativity. Energy equals mass times the speed of light squared. But hidden within that equation was a secret about time. The faster you move through space, the slower you move through time. This is called time dilation. At 90% the speed of light, time for you would pass at less than half the rate of someone standing still on Earth. While you experience a single year aboard that ship, decades could pass on the world you left behind. You would return younger than the friends you left behind. This isn't fantasy. This is physics. And we've already proven it. At CERN, particles called muons are accelerated to near light speed. These particles live longer than they should, because at those speeds, their internal clocks slow down, exactly as Einstein predicted. But speed isn't the only way to bend time. In 1915, Einstein revealed something even more profound. General relativity showed that mass and energy don't just exist in spacetime. They warp it, bend it, shape it.
The sun's mass warps the fabric of spacetime so deeply that Earth doesn't orbit by force, it follows the curve.
Clocks at higher altitudes, farther from Earth's mass, tick faster than clocks at sea level. Gravity literally slows time. Your GPS relies on this. Without correcting for time dilation caused by gravity and speed, your location would drift by kilometers each day. So we know time can stretch and compress. We've measured it, relied on it, built technology around it. But can we control it? Can we build a machine that doesn't just experience time's flexibility, but exploits it? The observable universe stretches 93 billion light years across. Even light itself would need eons to cross it. But what if space itself could be folded? What if two distant points could be connected through a shortcut, a tunnel through spacetime? This is a wormhole, an Einstein-Rosen bridge, a theoretical passage connecting two separate points in spacetime. In 1935, Einstein and physicist Nathan Rosen found that the equations of general relativity allowed for these bridges. If you could enter one, you would traverse a tunnel where the normal rules of distance collapse entirely. You could emerge light years away, or, theoretically, at a completely different moment in time.
Here's the key. If one mouth of the wormhole experiences time differently than the other, the bridge doesn't just cross space, it crosses time.
Place one mouth near a massive object where time slows. Wait, the two mouths now exist at different points in time. Step through one end and you emerge from the other. Not just somewhere else, but somewhen else. A time machine. It's elegant, it's mathematically consistent, but there's a devastating problem. Wormholes, if they exist at all, would collapse almost instantly, far too fast for anything to pass through. At the quantum scale, spacetime itself is a churning foam, tiny wormholes blinking in and out of existence trillions of times per second. To hold a wormhole open, you would need something called exotic matter, matter with negative energy density. Exotic matter would push spacetime apart instead of pulling it together, the opposite of gravity, and we've never observed it in nature. Though the Casimir effect shows that quantum vacuums can produce negative energy conditions, a tantalizing hint that exotic matter might not be impossible. Physicist Miguel Alcubierre proposed warping space itself. Inside the bubble, you're not moving at all. Space moves around you. And because you're not technically exceeding light speed locally, relativity isn't violated. Initially, the energy required was absurd, the mass energy of Jupiter, but subsequent refinements reduced it dramatically. Warp drives and wormholes are deeply connected. Both require bending space-time. Solve one, and you may solve the other. We stand at the edge of understanding, where physics meets imagination, and the possible meets the profound. Black holes are the most extreme time machines the universe has ever created. Their gravity is so intense that space-time curves without limit, and where space-time curves, time slows. At the event horizon, the point of no return, time nearly stops relative to the outside universe. Hovering near it, you could watch centuries unfold in the universe beyond, civilizations rising and falling, while only hours pass for you. A rotating black hole, called a Kerr black hole, has a ring-shaped singularity, and some solutions suggest you could pass through it. Theoretically, passing through could transport you to another region of space-time entirely, another place, another time, perhaps another universe. Penrose diagrams map the causal structure of space-time, revealing paths that mathematically connect to other time-like regions. Closed time-like curves pass through space-time that loop back to their own past. They're permitted by Einstein's equations. Physicist Frank Tipler proposed that an infinitely long rotating cylinder would draw so star-like would form around it. Cosmic strings, hypothetical defects from the early universe, could also create time travel conditions if two passed each other at high speed. But time travel to the past unleashes terrifying paradoxes. If you travel back and prevent your own birth, who traveled back? Some physicists propose that the many worlds interpretation resolves this. Every time travel event creates a new branch, an alternate timeline. You wouldn't change your past, you'd create a new universe where events unfold differently. Your original timeline remains untouched. The Novikov self-consistency principle states that any time travel event must be self-consistent. The past cannot be changed. Every action you take in the past would be an action that always happened. You can't change history, because you never did. Stephen Hawking once threw a party for time travelers, but sent the invitations only after the party was over. No one came. Hawking proposed the chronology protection conjecture, that the laws of physics conspire to prevent time travel to the past, protecting cause and effect. Quantum calculations suggest that the energy required to maintain a time loop would become infinite at the moment of closure, destroying the machine. The debate rages on. Is the universe self-protecting? Or are there loopholes in the laws of physics that we simply haven't found yet? The answers may lie at the intersection of the very large and the very small, where gravity meets quantum mechanics. At the quantum scale, the universe plays by different rules. Particles exist in multiple states simultaneously, cause and effect blur. In quantum mechanics, particles don't take one path, they take every possible path, and reality emerges from the sum of all possibilities.
Quantum entanglement links particles across any distance. Change one, the other responds instantly, as if space between them doesn't exist.
Quantum computing harnesses these bizarre properties, and some researchers believe quantum effects might hold the key to understanding time itself.
The holy grail of physics, quantum gravity, a theory that unifies space-time with quantum rule is.
Loop quantum gravity proposes that space-time is woven from tiny loops of gravitational energy, a quantum fabric knitted together. String theory offers another path. All particles are vibrating strings, and the universe may have 10 or 11 dimensions, most curled up beyond our perception. We are one theory away, one breakthrough that could unify everything and finally reveal whether time travel is possible. If we could generate and control exotic matter, even in microscopic quantities, the door to engineering space-time would crack open.
It might start small, a flicker, a ripple in the fabric of space, the first artificial distortion of space-time geometry.
A window no bigger than a marble, but a window into the underlying structure of reality itself. The technology would demand the collaboration of every scientific discipline: physics, engineering, mathematics, computing, humanity's collective genius. A stabilized wormhole, a persistent, traversable tunnel through space-time. No longer theory, now technology. The first traveler would not carry weapons or flags. They would carry the weight of every question humanity has ever asked about time.
One step across a threshold that separates everything we've been from everything we could become.
Inside the bridge, time and space dissolve into something new, something we don't yet have words for.
He emerges not into a different place, but a different age. 10,000 years of human progress, witnessed in a single step.
And return, carrying knowledge of what time truly means. Not a river, not an arrow.
Physics has already pointed us toward. The question is not if, but when.
Time is the deepest mystery of the cosmos, and for the first time in human history, we are beginning to understand it.